We present MaskAdapt, a framework for flexible motion adaptation in physics-based humanoid control. Our framework consists of 2 stages. We first train a base policy that acquires a foundational motion prior. To this end, we train it with stochastic body part masking and a regularization term that enforces consistent action distributions across masking conditions. This yields a robust motion prior that remains stable under missing observations, anticipating later adaptation in those regions. In the second stage, we train a residual policy on the top of the frozen base controller to modify only the targeted body parts while preserving the original behaviors elsewhere. We demonstrate the versatility of this design through 2 applications. First, in motion composition, we learn a residual controller that applies targeted adaptations while keeping the remaining body parts unaffected. Here, we show a motion composition example that combines jumping and alternating kicks. The controller first masks the lower body to elicit alternating kicks in the legs, then unmasks the lower body and masks the upper body so the legs revert to jumping while the upper body switches to the adapted motion. By continually swapping the masked regions, the adapting motion is layered interchangeably. The controller creates an expressive combination of both skills. Next is an example that adapts locomotion to a rotating arms motion. The controller demonstrates fine-grained control by first masking both arms, then unmasks only the left arm, allowing the rotation to persist solely in the right arm. Another example is the aim and sneak. The policy remains inactive when no region is masked, producing only the aiming motion from the base controller. Once the lower body is masked, a sneaking motion emerges in that region, creating an intuitive shift from the base action to the adapted motion. As the masking configuration continues to vary, the character exhibits smooth, progressive transitions across different body parts. Our method enables various goal-driven and complex scenarios, such as reaching target locations, striking objects, following target directions, and composing multiple motions. It also demonstrates applicability to real humanoid robots. The second task is text-driven partial motion tracking, where the residual controller follows localized kinematic targets derived from text inputs. A pre-trained trajectory generator converts a text command into short horizon predictions, which provide body part-specific goals for the residual controller to track. Here, we present a text-driven partial motion tracking example layered onto a walking sequence. Given a sequence of user instructions, raise right arm, flap like a bird, cross arms, the trajectory generator produces localized kinematic targets for the relevant joints, and the residual controller tracks these targets in real time. This results in clean, semantically aligned arm motions that blend smoothly with the underlying walk cycle. Here, we show a rollout where both arms are masked, generated using a base policy trained without the Mask-Invariant loss. Without this regularization, the policy collapses into highly repetitive, looping motions. A similar collapse appears when masking both legs. The policy falls into narrow, repetitive patterns. With the Mask-Invariant loss, however, the policy preserves diverse motion and maintains coordinated locomotion even under heavy masking. And it also retains a level of motion diversity that matches that of the unmasked baseline. Our framework outperforms CML across various motion composition tasks. In the jump and alternating kick example, CML on the left produces delayed lower body kicks, whereas our method on the right aligns the adapted kicking motion with the base jump. In the locomotion and rotate arms example, CML shows visible artifacts and incomplete arm rotations, while our method generates clean arm rotation behavior on top of stable locomotion. In the aim and sneak example, our method produces more natural and varied combinations of the 2 motions. As arm motion demands increase, both CML and the from-scratch model fail to maintain the underlying walk. CML develops intermittent step interruptions and an unstable gait, while the from-scratch model cannot sustain walking. Our method, however, preserves stable locomotion throughout. Our method may struggle when conflicting motions are assigned to closely related body parts. For example, combining a kick on one leg with a jump on the other can produce unnatural motion. Thank you for watching.